In this lecture, we shall be looking at a rather different kind of engineering. Nature has been developing life forms for a very long period of time, and we shall be taking an engineering view on how things move. It would, of course, be wrong to imagine that we can take over the same ideas, lock, stock, and barrel, from engineering to zoology or anatomy, or for that matter, the other way around. But there's a good deal of common ground stretching out in certain directions, including aspects of motion, and that's what we shall be talking about. There are nowadays many important and rather different fields in the general field of bioengineering, and we shall be looking at certain aspects of this. But we'll be talking mainly about the motion of animals and of human beings, and also a little bit about biomedical engineering, which is the application of the principles that are involved in motion to the study of and the practice of medicine. We find, of course, that applications in medicine, known as biomedical engineering generally, are very wide, and there have been striking successes in recent times with successful operations which have put implants into people who've had problems with their joints and so on, the replacement of joints, new aids for the disabled, new surgical techniques, and new scanning machines, and cooperation has really paid off. So let's start with an idea which is central to most engineering machines, the idea of the wheel. Now, the wheel is virtually non-existent in nature. There's a problem in that because if we have a jointed structure like our body, we cannot easily see how blood or nervous signals can be transmitted across a joint that's in constant rotation. And yet, of course, I can turn my hand in a circle and keep on turning it, and you might think that that corresponds to a constant rotation and things going around all the time. But in fact, if I exaggerate the motion a little bit with this slightly extended arm, you can see that although the hand does actually travel in a circle, it doesn't rotate. But the hand points in the same direction, and in fact, the motion is one of translation. So that's one of the successful kinematics in the joints that we and many other animals possess, which allow rotation to take place, but in that rather special way. And so it is that without the wheel, the problem of locomotion on dry land has led to many different and fascinating solutions, and we shall be looking at some of these. Take crawlers, for example. The earthworm crawls along quite cheerfully, and he does so by compressing his body like a concertina in parts and moving other parts forwards and backwards. Waves pass along his body. If something is handy to push against, then he will push against that and take advantage of the action. And here we have a little earthworm from, I think, Mr. Coates' back garden, recently arrived, and he's on the smooth patch of land just now, and he's found some convenient anchors to lock himself against, and he will push against it. Shortly, if he keeps going in that direction, he'll come on the rough patch of ground, and he may go on it a little way, but you'll soon find, I think, that he doesn't like it very much, and he's just discovered that it's perhaps not that attractive, goes around the other way, and decides it's generally a bad job and moves away and constantly explores. You can see the compression waves moving up the body and the bends. He's pushing against the little stops on the top of the field of view. Snakes, too, prefer to have objects to push against, and if they can maintain the same shape as they glide forward, then the results can be spectacular. And we have a short film of the snake, which we can show you, firstly moving in a nice gliding path in a very fluid manner as that adder moves forwards, as though he's flowing around the corners. And then shortly after he's finished his track, we'll see a very remarkable kind of motion of the rattlesnake, or the sidewinder as it's called, sidewinding away. He picks his body up from the floor, moves it sideways, puts it down again, and leaves those tracks behind in the general direction in which he wants to go. Now, we not only have some films of snakes, but we have some real live snakes for you to look at, and if you like to hold. And if I could take the first snake, called Lockett, I think, from Sheila. There's a nice little python, and at present she's exploring the scene, crawling around my hand. She's able to hold her head up by stiffening the muscles, and if you would like to take the snake and just see that it's quite safe and in fact fairly active, and you can hold that for a minute while we take this rather larger snake from Sheila. This is about 1 year old, I think, Sheila, is it? And a beautiful python, an Indian rock python. Underneath you can see the little scales, I think, if I hold it up, which actually connect with the ground and lock the snake as the snake is pushing forward in these compressions and expansions. And in fact, it's finding out where the top of my arm is just now, slowly going up there. If I put it down on the ground, then we may see that it's doing some serpentine crawling, which means forming loops at the top of the body, moving forward as the loop goes backwards until the loop falls off the end of the tail. So do you think he'll go, or rather she? It's Lucy, I believe, in this case. She's not very keen, you can see, to let go. She's locked herself around my arm there, but I think a quick twist and we can get away, and we will see if she can... She's found her own tail, I think, now, and perhaps is a little surprised by that. The floor, of course, is rather smooth, so there's not very much purchase for Lucy to get hold of, but she's exploring gently the scene, and when she sticks her tongue out, she's sensing the world outside, smelling it, and generally getting an impression of the atmosphere before she makes a move forward. So now if we can collect Lockett over here and hand Lockett back, thank you very much, that's a brave act, and give Lockett back to Joanna. And now Lucy has returned to base as well. So there we have some striking examples of motion without any legs. And we have in the next film a little demonstration of something that has a great many legs, showing how cleverly the young chap in question can move a rather large number of legs. This, in fact, is a millipede, and he's moving along busily on his daily rounds with a very large number of legs, moving in a very coordinated way. You can perhaps see the waves of the leg motion passing up and down the body as he goes. Now, there's a close-up, and the interesting thing is that it's so highly coordinated. If you can imagine how you'd control that, a very large number of legs moving forward like that, and you can see that the millipede has solved his problem. Now, crawlers. We'll come to our walking later on, and we'll perhaps get a few volunteers to do a little run for us to do with human locomotion. But before we do that, let's look at some of the other inhabitants of the animal world, and next look at swimmers, who show, if anything, even more variety than the crawlers do. There are the rowers, of which swans and ducks, I suppose, are the best known. You must have seen swans gliding elegantly along on the surface, and you will know, of course, that underneath that elegant upper region, the legs are paddling away busily down below. And we have, in fact, a highly extroverted duck called Francis Drake, which Sheila has brought along, and we're not going to put him in a very large tank in case he tries a sudden aquatic takeoff. But he sits there. Oh, now he's trying it now. Now, he's a real seed stealer, this, and makes comments on the lecture by going quack, quack occasionally, and will possibly dive and see what's at the bottom, see if there's any food about. There's a nice dive. And the legs, of course, if he had a long distance to move, would be busily working away. And the legs are extremely well designed, as you can see, as oars. They go down in the right direction, and they've got nice paddles at the end. Now, it's much more difficult to get Francis out, I think, than it is to get Francis in. So I'd like to ask you, Sheila, if you wouldn't mind taking Francis away before he gets too excited. Fine. Thank you very much. Now, we have a short stretch of film which will show a number of different kinds of swimming motions. And if we start that going, then I'll just comment on the film as it goes. First, there's a little water beetle, an expert rower, long rowing strokes sticking out from the side of the body and propelling himself forward in a series of pulses. A nice, easy action. Then we have a jellyfish, which I suppose is partway between rowing, except that now it's a circular rowing action, and jet propulsion. It's pushing the water back quite quickly compared with its speed. Another jellyfish doing perhaps a little more jet propulsion there than previously. And then we have, following this scene, you'll see an octopus which is darting away rapidly, and it must have been frightened or alarmed. It expels ink. And that fluid motion and the other water it expels backwards by the principles of momentum we talked about in the previous lecture drives itself forward with, as you can see, quite rapid accelerations. The next one is a ray, which is a very elegant swimmer, and in fact swims in a sort of flying action and uses the wings rather flapping, in a rather flapping mode, rather like a bird. And you can see it's quite gentle at the moment and rather elegant. Good steerage there. And finally, the great performer, the otter. The otter moves almost everything, tail, body, head, and his paws go busily away. Extreme maneuverability and rapid acceleration as he goes about looking for his dinner. Now, most fish, of course, oscillate as they move, and they use the oscillation to provide the propulsion. The form of oscillation, the detail, will vary with the shape of the fish, naturally. And long, thin fish, or eels, oscillate along their entire length, and we can show you, we hope, an eel which is about to do that. It's slightly dormant when we tried it earlier today, but with any luck, we can get him to show a nice pattern. And in fact, Mr. Coates has done the trick, and the eel is wriggling away. The motion is carefully phased from the head to the tail, and it's that phasing which actually determines the propulsive force. He's taking an interest in what's happening on one side just now, but if we give him a little stir again, perhaps turn him round, then away he goes and shows his paces. So that's how long undulating fish move forwards. We can also show you a slide of something like that, which in fact is a butterfish, not quite as long as the eel, but with a rather similar action. This is a series of pictures that have been taken at consecutive instants, but they've been printed side by side so you can see what happens to the fish in general. In reality, he'd be moving forward more or less in a straight line. And the first thing to note is that the head doesn't move its angular position all that much, not nearly as much as the tail does. In fact, most of the action is in the rear half, and it flicks its tail from side to side in a carefully phased way, this being the starting point. Number two, it's moving the tail inwards and across to the other side with a series of flicks, and away it goes at, no doubt, a very considerable speed. The shorter, fatter fish also oscillate the tails and to some extent the bodies, but perhaps rather less effect than the long, slender swimmers. And here we have a couple of carp who were introduced to each other just a day or two ago, and they seem to be extremely friendly. They move along gently from one side of the tank to the other, usually together. The colored one is a Japanese koi carp, and the other one is an ordinary or garden carp, I suppose you might call it. And here we can perhaps produce a motion by just disturbing him slightly and moving it along. Then we might be able to see that in slow motion if we can get a replay of that, and you can see the oscillatory motion of the fin taking place and see the details of the action. So if we just look at the screens for a moment, you'll see something happening. And there goes the koi carp to one side. And shortly he'll now he's stationary. He's past that point. So I hope you could see this carefully phased oscillation of the fin taking place. In fact, the hydrodynamic design of fast accelerating or fast swimming fish is excellent, and we can show you a slide which confirms that point. The upper picture is that of a trout, which is a very fast accelerating fish, And the lower slide is that of a modern low-drag airfoil, and you can see that there's a remarkable resemblance between the two. Of course, there are different kinds of airfoils and no doubt different kinds of trout, but the resemblance here is extremely close, and the variation perhaps is not all that great. So there we can see that nature, in fact, has developed through the evolution of the years the shape which has been confirmed by aerodynamic engineering to be an excellent shape for fast propulsion. Well, so much for fish. Now let's have a look at birds, and first look at birds gliding. And we have a bird which can be raised in a hand and give an impression of gliding. It's a nicely stuffed seabird, and of course it's heavier than air, so like all birds, so that it can't stay up due to buoyancy, and it has to do some work to do so. There are various kinds of flight, flapping flight, which we'll look at shortly. But let's first think about gliding flight, and assume that the bird is gliding in still air, no wind. Obviously, it will lose height unless there's some force there to keep it up. And of course, the force is generated by the wings. And in the outstretched position, and with a good angle of attack, i.e. with the nose pointing up and the wings pointing up, he can move forward through the air, dropping a little as he does, and the airstream going past the wings, rather like an aircraft wing, generates lift, and that allows the bird to stay up for quite long periods and travel very good distances. So the seagull is well designed for gliding purposes. Possibly the best gliders, or amongst the best gliders in the bird family, are vultures, who are quite expert at glides, and it has been recorded that one vulture in search of prey traveled 50 miles gliding in 90 minutes by cunning use of various thermal currents that he was able to take advantage of. And the way that works, of course, glider pilots do it all the time, is that as the bird may lose height in a straight glide, if he encounters a thermal current going up due to some heating of the ground down below, he can take advantage of that by turning into it and going up in a spiral, and so gaining height until he can begin the next downwind glide, so that he's well attuned to the variations in the air that make long-distance gliding possible. The albatross, let's pretend this is an albatross, does something even more cunning than that due to practice and evolution. And he takes advantage of something which is not an uprising current of air, but it's variations in the horizontal wind. And if there's a wind blowing over the sea, and the albatross flies mainly over the sea, then it turns out that the wind speed is larger as you get higher, and it's less near the ground. And the albatross, who is well informed about boundary layers, is able to take full advantage of that. Suppose the wind is blowing in that direction, from this side to that side, and this is an albatross. And what the clever old albatross does is to start gliding with the wind, and he loses height as he does that, and he's traveling in fairly high speed wind up at that point. The wind's going in that direction. So his airspeed is rather less because of that. Now, he'll lose height, and when he gets down to the lower region of wind speeds, somewhere down near the sea, then he does a turn into the wind. The wind is now going against his direction of flight to an extent. That means his airspeed is higher. That way he gains lift, and he climbs as a result of the higher lift to a point where he can begin the next downwind glide, and so progress in a series of curves like that. The downwind part, of course, being much longer than the upwind part. So the birds are very able to take advantage of the natural environment in which they live, and they've learned how to do these various tricks. Now, we'll have a short film, I think, next of gliding flight, which will illustrate two very practiced gliders. The seagull begins, and if we have this seagull in position there, then you can see that the two things are really very similar. And now we have a vulture, which is taking off. You can see that it's generating lift by the feathers, which are extended at the tips of the wings, and presumably he's now doing some gliding flight on a thermal, perhaps, and turning corners as he does so. That can be, you can see the wings turned up at the tips, and that's the lift force which is bending them and holding the bird up very largely. Now, flapping flight can be complicated, and here we have a little hummingbird. I'll show you a slide shortly of the details of the wing action. The wings beat at about 40 times per second, so it's a very high-speed operation. And he's managing to hover, stay practically still in the air as he sips the nectar. Now, if you look carefully at the wing motion, we'll look at that with a picture and a slide in a minute. This is a kingfisher, a different attitude of hovering, the wings beating in a slightly different way, but again, a result which enables the bird to stay there and look around and see what's happening. Now, the slide that we'll show you is that of the hummingbird first, and it's interesting because it shows how well the bird adapts itself to the condition. It's a very small bird, of course, and the way the wings work is rather like a figure of 8, as shown in the diagram there, except that the hummingbird does a very clever trick between the forward and downward stroke, in which the section of the wing, rather like an aeroplane wing section, is pointing forward and slightly upwards of the way that the wing generally is moving. That generates lift. That's the lift force up in that direction, small amount of drag. Now he keeps that up, but when he comes on the backstroke, then he turns the wing right round. The wing is very flexible, and now it's pointing in the direction that it's going again, but with an angle of attack, which means that the lift force is again upwards. So both on the downbeat, and which is the forward beat, and the backward beat, there's an upward force which holds the bird up, and the drag force oscillates a little bit, so there's bound to be a little bit of horizontal motion going on with the bird as well. That's so small that it's really rather difficult to see. Now, the other and more familiar kind of flapping flight, of course, is straightforward flight, and with the next slide, we can show you something of what happens with that. These pictures were drawn from photographs, so that they're not directly the bird in question, but they're a pretty good picture of what happens. The bird is a large condor, and he's moving from that side to that side by flapping his wings, which produce both the lift and also the propulsion. And the trick is that on the downstroke, which is the power stroke, then if you look at the section of the wing, say halfway along towards the edge of the wing, it's so arranged here that it's got, again, a positive angle with respect to the direction of the airspeed, which is here. That means that he gets a lift pointing forwards. That not only keeps him up, but it drives him forward. The bird, of course, is traveling more or less in a straight horizontal line. It's a section of the wing we're looking at. When the wing gets to the bottom, it comes on the upstroke, and then the bird changes the angle of attack, more or less in direction with the airstream itself, the direction it's moving through the air. So there's very little lift. And that's a recuperative stroke, if you like. The wing may be furled, and no lift is generated there. And then it gets to the top of the stroke and starts the cycle again. So that by that action of the wing, and again the twisting action of the wing, the bird is able to keep itself up and also drive itself forward with a simultaneous action. Very clever, you may think that. We can, in fact, we'll show you one more slide, I think, before we have a demonstration. This is a sparrowhawk, and I show it because it's an interesting example of the way in which nature's adapted itself to very high efficiency aerodynamic design. The sparrowhawk, as well as having a full array of feathers all over, as you can see, has some rather complicated stuff in this region of the wing. And they turn out to affect the detail flow of the air over a wing in such a way as to produce high lift, the right sort of boundary layers to generate lift, and they're all there in the bird, which is extraordinary. And then you notice that it's in a posture of high lift at the moment, that there's a cascade of wings, i.e. the feathers at the extreme part, and again, that is probably very good for the aerodynamics of lift, and also, of course, it's very complicated. Now, we do have a bird which we can show you. It will shortly fly, one hopes, flapping its wings in straightforward flapping flight across the theatre. It's a little temperamental. We hope that somebody in this region will be able to catch it when it lands. Mr. Coates is poised, the bird is wound, and if we release it, we can see the action. Oh, in fact, that was a beautiful shot. Excellent, Bill. Thank you very much. Now, we'll... Would you like to do another? Okay. No. Sorry. We'll do the slow picture of that, which I think was caught well of the cameras. Was it? Yes. Fine. They got that fine. So now, if you look at the screen, you'll see this in slow motion, and the flapping motion of this little bird's wings. It's turning a corner. I'm not at all sure how he does that, but in fact, I'm not at all clear how it flies at all, come to think of it, except that it's obviously simulating the bird's variation in the angle of attack in this ingenious little toy. So there we are. That's a real model which works up in the real air. Well, I think we ought now to turn and have a look at how we move around ourselves. But before, we have one more excerpt of a film to show you, showing perhaps the more vulnerable maneuvers in flying, i.e. takeoff and landing, and you can see what a great contrast there is between two different kinds of birds. So if we have the next piece of film, you can see this mighty swan walking on the water and then beating its wings and taking off. He has managed the takeoff rather well. Sometimes they don't, and here's a little puffin. Coming down perhaps in a slightly less elegant way and looking for a safe landing spot on a very crowded beach. So almost infinite variety of patterns of motion will follow that way. Now let's look at that marvelous machine, the human body. Here we have a skeleton. It's not a real skeleton, it's a made-up skeleton. But it's made up in a rather special way. It represents a 6-foot man weighing, we think, seemed to be about 15 stone when we lifted him up this morning, so that not only is the dimensions about right, but the weight is about right too. But the thing that it's interesting to look at is that this is a model in which the joints have been put in a very similar way to the human joints. If I take the arm, for example, I can move out the shoulder in the way that the shoulder can move out. I can also turn, giving limited motion of the shoulder, which you all have. And then if I show the elbow movement by just putting my hand against the hand here, I can move that in that direction, giving an elbow motion, and no doubt I can produce a wrist motion as well. So there's a great deal of articulation which we possess represented in this model. In fact, it's been calculated that altogether there are more than 200 joints which are under control in the body, under the control of one brain, that is, and they all can be operated from that single source, and a lot of them can, of course, operate simultaneously. So there we have a model which has to be used in many applications, not only medical but also engineering, like models in cars which are subjected to crash testing and so on. Now, of course, if we have a body of that kind, then we think about what clothing it has to wear. Most of us wear clothes most of the time. And the tailor's art is something to think about, because you have to move the joints and do that inside the clothes. Let us show you two different kinds of suits, one of which is rather spectacular. And if we can get him in, you can see he's the very sizable suit. It is, in fact, a replica of the suit worn by Colonel Buzz Aldrin, who was in the first party to land on the moon. And the thing about that's worth noticing is not just the size, but the fact that, of course, that it is pressurized, and the designer then has to provide for the articulation of the joints, even when there's pressure inside. And to go into that would take us too far. But you can see it's an important thing. It's no good just getting on the moon and then sort of standing perfectly still, like a blown-up balloon. And the design of that suit, a very expensive suit, accommodated those motions. And then we have a small space person who's also, I think, waiting in the wings. And if we can open the door and get Sarah in, you can see that we can also get the small spacesuits made up. Sarah has not yet been to the moon, but perhaps she's hopeful that she will. So the suit is not precisely a replica like that, but you can see that it's a jolly good suit to have. If you'd like to stand there for a minute, Sarah, we'll get in the next suit wearer, and this time it's 400 years old, genuinely 400 years old, and we now try and persuade the gentleman inside it to come inside. The knight in shining armour. will shortly approach. I'm not sure that he can see too well through the visor, but if you come forward here and stand there for a moment, then we can just have a quick look at the way that the suit of armour is actually constructed. Because here the tailor, or in this case the blacksmith, has had to design the joints so that the shoulder can move, and I think the shoulder is movable, the elbow can move, the wrist can move. The total weight is probably about 60 pounds or so, but the stability of the body. So there's a reasonable degree of mobility involved. Now, if you'd like to raise your visor, sir, which is not so easy as it looks, then you may recognize the smiling face of Alan Jameson, my colleague from Newcastle, inside, and you may want to take the suit back to Newcastle, Alan. But in the meantime, come over and it's, we can't resist introducing the 4 centuries old knight to Sarah, and then I think they'll walk off happily hand in hand, perhaps. So if you'd like to go off in that direction. There are some very interesting aspects of the way we move, which relates to the joints I've been talking about. Take walking, for example. Sounds simple enough, but we walk in a very coordinated way, and putting the left leg forward, the right hand moves, left leg, right hand in phase, and so on. And we keep one foot on the ground almost all the time, so that this foot, the rear foot doesn't come up until the first foot is down, so we keep in a state of balance. Running, though, is different, and we do have, I think, a volunteer who's got his gym shoes on, and we'll try and take a picture of his running action as he runs as far as possible. You can get up speed, perhaps by... Your name is?
Anand.
Anand. Get up a little speed, and don't be afraid to bounce as you go. And you'll see in the slow repeat afterwards that it's an entirely different action. So speed over to just to the right of the camera there, and you'll try and take pictures as you go. Off you go. Now, thank you very much, Alan. You may like to see yourself on the monitor. You can probably see up there, and we'll play that back in a minute, and we'll see that we can get pictures, I think, in which he's coming now, and I hope you can see that for a large part of the cycle he has both feet off the ground. And in fact, you can work out the speed at which he has to break into a run, because the only force he has downwards to compensate for the motion in an arc of the body is his own weight, and that determines the maximum speed that somebody can walk without actually getting both feet off the ground. So thank you very much, Anne. It was a very good, successful run. Now, let's look at some of the surprising dynamical effects of human locomotion, which we can demonstrate with the help of a few volunteers using this remarkable Kistler force platform, which is a kind of very high-tech weighing machine. It will weigh people, but it will also register sideways forces in 2 directions, and it'll register torques about 3 axes, 1 up and 2 horizontal, and we have to get a volunteer to try and help us with this. Now, I'll explain that what we're going to show in this case is the vertical force only of the foot as it crosses the force platform, and although this plate can do very much more. And first of all, we'll have a demonstration of walking across it with, again, the volunteer who knows the score. Your name is?
Max.
Max, okay, Max. If you'd like to walk across that and put 1 foot only on the platform as you go, I'll come around to this side, and we can see the effect on the screen. If you look at your monitors, then you can see that we'll actually get an imprint of Max's footprint on time, as it were, taken as he walks across the platform. Don't go away, Max, because we haven't quite finished it. The footprint has 2 peaks in it. One is the heel down, the other one is the toe off. And the characteristics, the details of that can be very helpful in clinical diagnosis, for example, of the action of the joints. And this machine has now got that recorded. Now, if you'd like to repeat that, but this time running across, then we can see, just go across there and make another start. And this time, see if you can get a run up and put 1 foot again firmly on the plate as you come across. And now you can see that we've got a very different picture. Thank you very much, Max. We'll talk about that for a minute. Now, of course, the force is very much higher than it was beforehand, and we could go on with the experiment and show many other variations than that. The actual value of the force isn't registered there, but for running it would be substantially higher than body weight. For jumping from a height it would be several times higher again. Now if you could have another volunteer, we can show something even more remarkable on the plate. Somebody, would you like to come down? Your name is? James. James. If you stand on the plate, James, and just stand there, do nothing. If you like to face the other way, then we can pick up James's heartbeat. James's heart, of course, is beating well and is pulsing blood out in an upward direction. There's a jet reaction to that on the ground. And if we do a little adjustment here, I think we can probably show the heartbeat taking place. Could you step off for a minute, James, please, and then step back on again? We've got to get the zero set up. Okay, back on. And if we may have to make a slight adjustment here to get the action complete. We seem to have lost the trace at the moment. So if you just hang on there, breathing gently while we change the controls. We may come back and try that again in that case when we get back to, there we get something coming in now. That's showing it. Thank you very much. That required a different adjustment. Just keep still. You're shaking everything. And if you like to breathe downwards rapidly, give a puff down, then you can see that the actual change in the breath coming out is shown on this extremely sensitive force platform. Your heart's in good shape, James, so fine. You can now step down if you like and come back to the seat. And thank you for helping. Now there's an even more remarkable development of this plate, which we can show you with another development which has been worked up by a DHSS research laboratory in Oswestry Street. And this shows not only the footprint or the variations in force in that way, but it will actually draw the force as a vector. You remember a vector is a quantity represented by an arrow, like a force. And in this arrangement, we can show somebody walking across the platform and display on the screen, superimposed on his foot, the vector action of the force. And that's something which is quite remarkable. And we have a volunteer, I think, for that. We're going to have somebody coming over. We're getting that. Set down for a moment. And we'll have somebody walk across and we'll show you on the screen then the way that the force actually varies in real time as the volunteer comes over. Could we have a volunteer? Somebody perhaps in this direction? Could we have that young man there perhaps? Now what we'd like you to do is just as Max did, if you'd start on one end of the walkway there and walk across and tread firmly with your right foot if possible on the plate, then you could see, I hope, as you went over. Could you do it again and put a good firm footprint down as you do it? Yes. Could you do it again, please? Right across. Foot down. And you can see that the little vector, which we can show you in slow. Have we got that? Okay. So thank you very much. We'll just show that now. It's going back. Fine. And the variation in the force is shown as he moved over. And you can see both the direction. Thank you very much, James. Thank you. And the little vector, I hope you noticed, was pointing in the direction of the leg, i.e. up through the knee joint and through that to the hip joint, so that the bending on both joints is minimized by the action, which is so dramatically shown there. Now, as well as measuring the forces involved in various forms of human motion, we need to know about the gait itself. Not only for research, but again for clinical diagnosis to determine how the system is working. And we have here a most remarkable machine which is being developed by David Michelson, and he in fact knows how to operate this better, I think, than anybody else does. So he's going to help us to get this set up. Now, the way it works is like this. Inside this box of tricks, there are three mirrors, one inside each window, and they're rotating at very high speed. The two outside ones spin about a vertical axis about 3,000 times per minute. And this one spins about a horizontal axis at the same speed. They emit light from the mirror, from the windows. The light is reflected back from that prism of glass that Mr. Michelson is now holding in his hand. And the reflected light goes back to these three mirrors. a signal is picked up the instant the light hits the mirrors, which is virtually instantaneous in the travel. And the angular position of the mirrors is then recorded. From trigonometry, the computer then can work out exactly where that little piece is and can do it at high speed, and we shall be registering the position on the XY plotter that I hope you can see as the light is moving. No connection except the light is driving the plotter forwards and backwards as Mr. Mitchelson moves it in those directions. Now, we need a volunteer to help us with that, and we've got somebody kitted out, I think, who's able to do it. So that if you'd like to come forward and tell me what your name is. Freya. Freya, okay. Now, if you come around. So, Freya, if you'd like to stand there, Dominic just behind me for the moment, and take the pen in your left hand, move it around a little bit, just get the feel of the action. Now, if you move that, and then what I'd like you to do is to write the word hello in the air, not too big, but nice gentle movements. And we'll see that the pen will actually follow the writing in the air and will spell it out on a sheet of paper. Fine. Would you like to go? Just write hello in the air. That's going well. Now you're writing freely, and do a nice round O at the end. You're doing it rather square. And there we are. That's very good. We can see what you said. Thank you very much. Of course, that's just fun doing it that way. But it has a serious purpose, of course, and the purpose is clinical. And now we have another volunteer, Dominic, who's got one of these things stuck in his head. And, or will in a minute have something stuck in his head. We now take this off and we imprint it on his forehead so that that's the marker, and the machine now should detect his motions. If he could stand just here on the yellow marker there, that's right, that between your 2 feet. And now he's facing the mirrors, and we'll ask him to stay still. It's impossible to keep your head still without swaying slightly, and the trace is now recording his swaying. Would you like now to stand on one leg? More difficult to keep still now. Would you like to close your eyes? And you can see that he's moving. If I give him a gentle push, then he falls right over. Fine, thank you very much. So small details of motion can be detected in that way, and the analysis of those motions afterwards can be very important. Let's now turn to a few examples of biomedical engineering as they involve the disabled, and we'll start with a look at a hip joint. We have a hip joint here for you to look at. This is a facsimile leg with bones containing it at one end, the hip joint at that point, which would fit in the plastic cup which is fitted in the pelvic bone and form a ball joint which has to satisfy very severe requirements of strength, stiffness, lubrication, durability, and reliability, and so on. And all that's been achieved by experience and by good design, cooperation between the surgeons and the engineers. The slide will actually show how the hip joint is implanted in the bone, and you can see that it's got a hook which goes down inside to secure it, and once inside it's securely locked and cemented there. And of course hip joint replacements are now very widespread and successful. The knee joint is a more complicated joint, and here we have again metal working on the plastic material, but the kinematics is more difficult than the hip joint. It has to provide for rotation of the knee and also a certain amount of twist and translation across the two surfaces. And so that design, although it may look rather simple, has been carefully calculated to provide for these requirements. We have also an artificial leg, a complete artificial leg, which is an Ottobock leg, in which the basis of the design is provided by a 4-bar linkage of a particular mechanical kind that sits here, which I hope you can see. If you look at the screens, you'll see the details on the monitor. And if the leg is rotated, then the motion of the joints reproduces to a very considerable accuracy the actual motion of the knee. It's also loaded in such a way that the knee is kept stiff when it should be kept stiff, and it's allowed to move when it's required to move and bend the knee. So if I just move over and do this heel down, toe off operation, then you can see that one could, in fact, if this were fitted with the right size and so on, perform a very natural motion of the leg with this, as opposed to the older versions of peg legs and with people just straight sticks and no articulation at all. So that's been a very successful design, and is constantly under development. We can show you next some heart valves, which again are the product of cooperation. And this is one such valve, which will fit in the heart. And then this is another one. I'll just explain before we show you a film of these actually in a heart, how the valves are placed. If we show the slide first, I think we can see the requirement. This is a heart which has actually been opened in the left ventricle. The heart on the left side has two compartments, the atrium with the blood coming in from the lungs, and there is a valve which prevents the blood going down into the ventricle until the flow is sufficient. That valve is called the mitral valve, and is marked in that position. The other valve releases the blood from the left ventricle into the aorta, which is the main artery of the body, and there's a second valve which is positioned there. In the case of the film that you're about to see, it's an X-ray film taken with the patient. Both valves had to be replaced because they were damaged, and if we now turn to the film, you can see the way that the action went. The upper one is the valve into the aorta, and the other one is the mitral valve. There is liquid being released inside the heart, which is to be tested for the closure of the valve. And the stain is not harmful to the heart at all, but enables the doctors to determine how well the valves are working. And these marvelous operations now can be conducted with considerable benefit from the advantages gained by the development of these little heart valves. Another very important development is represented by this arm. It's an arm for a child who has had an amputation, and it's operated by power. And inside the arm there's a little electric motor which can drive the thumb and the first two fingers. And if I just operate the motor, you can see that the closure takes place. And here it's opening again, done by a touch on a switch on the inside. In fact, the operation can be, that is, the switching can be done by myoelectric effects. Small electrical impulses from the remaining muscles in the arm will in fact activate the hand, so that the impulse to do it will in fact cause it to be done. And it's quite a good grip. As you can see, I could probably pick my glasses up if I don't break them in the process by just touching the two parts, and it's very versatile and on the arm very maneuverable. Another way of doing it is to drive it and to switch it by means of a shoulder harness, and in fact in practice this turns out to be very popular. The harness is put across the shoulders, and a slight movement then pulling the wire of the shoulder blades will open or close the fingers in the same way as I showed you a minute ago. So those developments, of course, are of great importance for people who are disabled, and they're constantly under improvement as the design and the manufacture improves. Well, finally, let's look at a few examples of the people and machines working together, some very simple ones, and after that, perhaps something which is a bit more complicated. And the first one we'll show you is somebody using 8 wheels for moving around, and we have somebody already kitted out who's able to do that. Perhaps I could come alongside as you're coming down the steps. Your name is? Charlotte. And Charlotte is an expert roller skater, but of course it involves considerable skill. If you'd like just to do a little demonstration turn on that, then she's operating with 8 wheels extremely well. Can you come back again, do you think? And of course the motion there, as most of you will know, I suppose, is from side to side, and that produces a forward thrust. Still obeying Newton's laws of motion, though. Thank you very much, Charlotte. That's very good. Good. We were going to get a volunteer for a bicycle, and I don't know if somebody's around who'd like to try their hands at doing a quick turn on this. Somebody on the aisle somewhere who's easily accessible? How about the young man there? In fact, if we start you off in this direction, perhaps, and you can drive out, then again, try and turn the corner there if you can. Mr. Coates will rescue you if it goes long. Then you can again demonstrate a very good combination of man and machine, which the Wrights in Dayton were experts at before they took to the air. Now, to turn from what are very familiar examples of man-machine interface, we will close with some examples that are extremely spectacular. And you will all have heard of the red arrows and of their great artistry in flying and with aerobatics. And I would like to introduce to you, to act as a commentator for the film that you're about to see, one of those very pilots whom you'll shortly see doing some amazing tricks in the air. So if you'd like to come in, Simon. Welcome again. Now I introduce the Flight Lieutenant Simon Bedford, who will run a commentary on the film, which will now come up on the screens.
Okay, the team are running in 7 of us here, the synchro pair having split off. And here we see the synchronized pair in what they call a boomerang cross. After they've left the stage, you see the remaining 7 running in now, and each one individually pulling out and rolling over the top. We call this maneuver rollbacks. The leader is calling each side alternately by our numbers, and then out you go and round back into the slot again. And let's have a look at it from inside the cockpit. It gives you some idea of what it actually looks like. In the meantime, the synchronized pair coming around doing their thing again in what they call a carousel, a closing speed of about 700 miles an hour. And at the end of it, we all get together again, all 9 of us, in a join-up loop formation. And there you can see on the right and left-hand sides, the synchronized pair joining in on the outside, so that by the top of the loop, at about 4,500 feet, we're all back together again. The smoke goes off, and then as we come down into the vertical, split into the parasol blade, or what actually we call spaghetti, and you'll see why.
Well, I'm sure we see why. That's a spectacular piece of flying in an excellent film. We'd all like to know how you do it, so if you wouldn't mind just talking to us a little bit about some of these things you've just looked at. First of all, what is the aircraft you fly?
We fly the British Aerospace Hawk Trainer.
Mm-hmm. Which is obviously a very versatile aircraft and well adapted to these complicated maneuvers that Simon's been showing. You work very closely with the other pilots, of course, in more ways than one, since you're right next door to them. Mm-hmm. Do you get to know them very well?
Oh, yes. We actually live out of each other's suitcases for most of the summer when we're on the road. And, of course, in the winter we're practicing together 2 or 3 times a day when we're with the planes.
There was a question asked after one of the lectures the other day, which I'd like to put to the Flight Lieutenant, and that's how you fly upside down. You spend a lot of your life flying upside down, I imagine.
Yes.
And yet that would seem to put the lift the wrong way. The lift would then tend to drive the aircraft down.
Yes.
If
you're going to fly straight and level upside down, then if you look at an aeroplane, you'll notice that the nose is sitting much higher than normal, and you actually have to increase the angle of attack much more so of the wing upside down, and it makes, unfortunately, for fairly inefficient flight.
Yes, but it's possible for short periods at any rate. Yes.
Yes.
As to the controls you have are obviously very, very versatile and sensitive. In the older days of aviation, there was the theory about flying with the seat of the pants, which means you pick up the accelerations of the body, I think. And does that still have an important part to play?
Yes, I think you could call it the seat of the pants. Certainly, by eyesight, in this particular job, you're flying very much by visual references from outside. You're looking at the chap next to you, and you're actually responding to any movement that he might make. Yes. So it is very much so, yes.
And is it as dangerous as it looks?
No, it's a con. It's an optical illusion. Not really an optical illusion. It is well practiced, very well rehearsed, and it is designed to look dramatic.
Yes. It certainly does. Thank you very much.
Thank you very much.
Well, we have one more example of a man-machine interface, which is of an entirely different kind, and I'd like to introduce Mr. Dennis Lord from the Atomic Energy Research Establishment. Dennis, welcome. Who's brought with him a master-slave manipulator used for picking up dangerous objects, small dangerous objects, but nevertheless not handleable directly by man. And he will operate from this end, which is connected only electrically. There's no mechanical connection to the sharp end here, which will be picking up dangerous pieces and putting them down very precisely. So now, if I could invite you, Dennis, to do your maneuver here with the machine, which we have switched on. you can see that Mr. Lord will be operating at one side, and with any luck, the robot arm at the other side will follow his instructions. To save some time, we've taken the cork off the bottle, but I think there's something in the bottle, isn't there? Yes. Good. Oh, good. It's very good. Well, thank you very much. Well, cheers. Cheers to you. Thank you very much. Tastes very well. It goes down very well. Well, we've seen a number of examples of man-machine interface. The connection between the two is very important. Machines are there as servants of man, and if they're properly designed and made and operated, then they can serve us all very well. We're coming now to the end of the series of lectures, and I would like to express my thanks to the many organizations and individuals who've contributed advice and much equipment to this and the previous lectures. The putting of the show on the road, of course, is entirely a team effort, and I would like also to express my thanks to members of the team, but particularly the Royal Institution team, led by Bill Coates, who've overcome every difficulty on the way, and Bill is just standing on the side there. To the expert BBC team, both in front of the cameras and on the scene here and behind the cameras, as you've seen downstairs, we've benefited greatly from their skills and expertise, so we owe them, I think, an expression of our thanks. And I'd like to give my special thanks to the team at Newcastle and my colleagues in the university there who've contributed advice and much hard work, especially in the workshops, in making up so many of the models that we've been able to show you in the course of these 6 lectures. And none, I think, has contributed more from that quarter than Alan Jameson, who went out in his armour a few minutes ago, and who I'm not, now seems to have entirely disappeared. Perhaps he's still locked in the armour, but we'll check him out afterwards. And finally, I would like to express appreciation, I think, on behalf of all of us, you and the people who've been helping, to the Royal Institution generally for the pleasure of meeting in this famous building. Thank you very much.